Hi folks, today we're going to talk about something kind of interesting. It's connected to the previous day's topic where we took equations of lines, we graphed them, we found the enclosed region that was bounded by all of the lines, and then it created a shape. And we shaded it and we identified the shape. And so today we're going to talk about solids of revolution. So we're going to be taking shapes that we get whenever we either draw lines from equations and figure out the bounded area, or we may plot points and connect them to make a shape on the graph. And we're going to create solids out of them, three-dimensional solids, by revolving them around an axis. So whenever you plot your points on a graph, we can create 3D figures by rotating it around an axis. Once we've determined the figure formed, we can then find its volume. So our steps today, and we've got 4 of them. First, you want to plot the points that are given to you and connect the points so that you can create a polygon. Make sure that you connect them with either a straight edge if you're writing in pencil, or if you're using Cami, then make sure you use the line drawing tool so that they're nice and straight. You then want to graph the reflection of the image over the given line. So you want to reflect it over the given line, and this given line, this is going to be the axis of rotation. Once you reflect it over the axis, you want to determine what 3D figure is formed after you do the revolution. And once you determine your 3D figure, you should have a volume formula in mind, and you can calculate the volume of that 3D figure. So example 1 says, find the volume of the solids formed by the given coordinates. So in example 1, I have 4 points, so I'll have 4 vertices of a polygon, which means that it'll be a 4-sided polygon. It'll be a quadrilateral. So I'm going to graph the point 0, 0, 3, 0, 3, 4, 1, 2, 3, 4, and 0, 4. So this is my figure. And what I want to do, there we go. What I want to do is I want to rotate this, or reflect it for right now, but then rotate it over the x-axis. So here's the x-axis. This is going to be my axis of rotation. So this graph right here of this figure, I'm going to flip it over. I'm going to kind of spin it around to the other side. So I want you to imagine that it's going to lift off the paper and it's going to flip over and be on this side. So I'm going to reflect it first. To reflect over an axis, you count the number of units to the axis. So 1, 2, 3, 4. And then you count that same distance past the axis. 1, 2, 3, 4. This point is already on the axis, so it doesn't need to be reflected. Same with this point. It doesn't need to be reflected. It's its own reflection. But this point is 1, 2, 3, 4 units away, so I go past the axis 1, 2, 3, 4 units. So here is the reflected graph. Now what's happened is that we've had this vertex right here. It's lifted through the air, through space, and it's come back over on the other side. And if I did a full revolution, it would go back under the paper, and then it would come back and be here. Same thing with this point. You lift it off the paper, and it comes through here, and then it goes behind the paper, and then it comes back here. So that's the revolution that we're talking about. And in order to draw the revolution, you end up taking these vertices that get reflected and are not actually on the axis, and you end up kind of giving them a curve through space. So it's going to curve down here, and then it's going to curve back around under the figure, so dashed lines. Same thing with this vertex. It's going to curve around here, and then it's going to go behind the figure. So once I have that figure reflected, and then I've drawn the actual rotation of that vertex all the way around, kind of makes an oval here or an ellipse, the figure that's formed is a cylinder. And now that I know the three-dimensional figure that's formed, I can use the volume formula of a cylinder to calculate the volume of this solid of revolution. So my volume formula for the cylinder is the area of the base times the height. The area of the base is pi r squared because the base is always a circle in a cylinder. I can pick out some of my values. So my radius would be this distance right here, 1, 2, 3, 4. So radius equals 4. The height of the cylinder might be easier if I kind of turn it to the side. The height of the cylinder is the distance between the bases. So that's 1, 2, 3 units. So I'm going to make sure that I label that on my figure. And now I can insert the dimensions into their proper place in the formula. So the volume equals pi times the radius of 4 squared times the height of 3. 4 squared is 16. 16 times 3 is 48. And 48 times pi is 48 pi. We don't have inches or centimeters or anything like that, so we just simply say units cubed. So in this set of notes today, you have to be able to draw three-dimensionally. So when we draw three-dimensionally, the thing that makes it look right is connecting these vertices with a curve in the front and a dashed curve in the back to show that you're looking through the figure. So let's look at example 1b. Example 1b, we want to graph the point 0, 0. 3, 0, 3, 4, and 0, 4. So the same 4 points. I'm going to go ahead and go over them in Sharpie so that you can see better. Okay. And it's important to know the axis of rotation. So we're going over the y-axis here. Here's the y-axis. That's what we're rotating around. So what we have over here, we're going to flip over and put here. What we have over here, we're going to flip over and we're going to put here. So these 2 points are already on the y-axis. They are their own reflection. These 2 points we need to reflect over. So 1, 2, 3 units to the axis. 1, 2, 3 units past the axis. 1, 2, 3 units to the axis, and 3 units past the axis. So here is the reflection. Now, remember that the points that were on the axis didn't really move, but this point reflected over here, so I'm going to draw it arcing over here. And then if you rotate it all the way around the axis, a complete revolution would come back around the backside. Same thing on the top. This point here would rotate over the axis, and then it would come around the backside. There we go. So again, what figure is formed? This is a cylinder. My formula for the volume of a cylinder is what we have written in example 1a, pi r squared times the height of the cylinder. I need to find the radius and the height. The radius would be this distance from the center. Notice that the center is on the axis of rotation. That distance to the edge, or I guess not to the edge, but to the circle, is 1, 2, 3 units. So the radius equals 3 units. The height, the distance between the bases, is 1, 2, 3, 4 units. So height equals 4 units. So I insert 3 for the radius. I insert 4 for the height. 3 squared is 9. 9 times 4 is 36. And 36 times pi is 36 pi units squared. So this is what it means to create a solid of revolution. Let's go on to example 1c. Example 1C, there are 3 points, which means our original figure is going to be a triangle, because 3 vertices means 3 sides. The origin, 0, 0, the point 2, 5, and the point 0, 5. So I have my go. My figure here. Let me go ahead and make it a little bit bolder. Okay. And we're rotating. We're rotating over the y-axis. So here's the y-axis. What we have on the right side, we're going to rotate and spin to the left side and then back. These 2 points on the axis don't get reflected because they are their own reflection, but this point will come over 1, 2 and past it 1, 2. So it will be like this. Remember that if a point lifts off the paper and reflects over on the other side, you must show that movement, and then it must go around the back side as well. So what figure is formed? This is a cone. The formula for the volume of a cone is 1/3 area of the base times the height. And the area of the base would be the area of a circle, so pi r squared gets inserted for the area of the base. So let's find all of the dimensions. The first dimension we need is the radius. That's the distance from the center of the cone to the circle's edge. So that's 1, 2 units. Radius equals 2. The height of the cone is the perpendicular distance from the vertex of the cone all the way to the base. So the center of that circle, that's a distance of 1, 2, 3, 4, 5. So the height equals 5. Keep in mind that this little arcing curve right here that shows the motion from this side to this side, this bit, it might be a little bit longer, it might be a little bit shorter, but this doesn't really matter. The height is from the vertex to the center of the base. Not to here, but to the center of the base. So don't count from here 1, 2, 3, 4, and then maybe a half, 4.5. That height goes all the way to 5, to the center of that circle. So when I insert the dimensions, I have 1/3 times pi times the radius of 2 squared times the height of 5. 2 squared is 4. 4 times 5 is 20. 20 times pi is 20 pi, and 20 pi times 1/3 is 20 pi over 3, and we measure in units cubed. Final problem today, example 1D. We have 3 points, so we're going to graph the point 0, 0 and 0, 5, 1, 2, 3, 4, 5, and the point 4, 3, 1, 2, 3, 4, 1, 2, 3. So knowing that I have 4 vertices means that my original figure created is going to be a triangle. So let me go over this and bold it a little bit. Okay. Now I'm reflecting or rotating over the y-axis. So here's the y-axis. Everything on this side is going to get rotated around over here and back. Everything over here gets rotated and spun around. It's easy when you show the rotation. So show the rotation along the axis, and that's helpful. These 2 points can't get reflected to the other side because they are their own reflections. This point needs to move 1, 2, 3, 4 units past the axis. 1, 2, 3, 4. So along with my 2 points that were their own reflections, there's my other figure. And this vertex lifted off the paper and got reflected over here. So when I show that reflection, I'm going to show the movement. And then in order to do a full rotation, it spun all the way back. So, what figure is formed? Well, that's not a nice figure that we have one formula for. That looks like a cone, but then a cone on the bottom as well. So there are 2 cones formed. This is a composite 3-dimensional figure, which means that our total volume will have to be either the sum or the difference of the 2 cone volumes. So because the cones are taking up different spaces, one is not laying inside the other, we're going to add the volume of the top cone and the volume of the bottom cone. The cone volume formula is 1/3 times pi r squared times h. 1/3 pi r squared times h. I have r's and h's in 2 places. I want to make sure that I have them correct for each cone, the top and the bottom. So here's the center. Here's the radius. The center of that circle going out to the edge of the circle is 1, 2, 3, 4. 4 units. So the radius is 4 for the top cone and the bottom cone. The height is the distance from the vertex to the center of the cone. And it's got to be perpendicular to the base. So this distance right here, that's the height of one cone, 2 units. And then this distance right here, 1, 2, 3, that's the height of the bottom cone, 3 units. So when I insert my dimensions into the formula, I have 1/3 times pi times the radius of the top cone, which is 4, squared, times the height of the top cone, which is 2, plus 1/3 times pi times the radius of the bottom cone, which again is 4, squared, times the height of the bottom cone, which is 3. 4 squared is 16. 16 times 2 is 32. 32 times pi is 32 pi, and 32 pi times 1/3 is 32 pi over 3. Next term, 4 squared is 16. 16 times 3 is 48. 48 times pi is 48 pi, and 48 pi times 1/3 is 48 pi thirds. And I didn't simplify this to be 16 pi simply because I'm adding with another pi over 3 term. So I need to add my numerators. 32 pi plus 48 pi would give me 80 pi. So my total volume is 80 pi over 3, and we measure in units cubed. So this one was a little different because the figure formed was a composite figure created by putting 2 cones together.